Okay, we're on. Whatever you said right now, it's being streamed. Huh?
Alright, good evening everyone. Thank you very much for coming. We're very excited to have you so numerous. I hope not too tight. We're also very excited to have Eric from CAN and all the development team here. And we're also very excited to have worked with Chico having a machine learning meetup on this, so getting into hand and live streaming. I am not going to spend more time talking about STEM because Eric's going to tell you all about it. I'm not going to spend more time telling you about Data IQ because the other Eric from our team is going to be presenting a project done in Data IQ BSS with STEM. We'll talk all about what we do. I think we just dive in and I hope you have a nice evening. Thanks very much again.
Bonsoir. Hello, thank you for coming. It's my first time coming to Paris, so I'm still enjoying all the wonderful things here, mostly the pastries that putting on some weights, which is great. Before I get started, I never know when I come to Machine Learning Meetup, I don't know the audience very well, and so I want to ask you, if you don't mind, how many of you are familiar with Bayesian inference? Okay, so quite a few of you. Okay, and are you guys familiar with R language? A lot of you. Okay, so some of my examples use R, so I want to make sure that I cover. Great. So maybe I won't spend so much time on Bayesian and speed through that a bit. So here's the plan. For today, I do want to say a few words why you should bother with Bayes. I know not everyone is convinced that that's the right way to do things. We have a very strong opinion on that. And also, if you like Bayes, why you should use C. And so then we'll talk a bit about Stan, the language. I'll show you a simple model. I'll build it up in R first, and then I'll show it to you in Stan. I want to demystify Stan a little because it may be a little mysterious at first when you start using it. And then I'll show you an example of a model that we actually use for a large book publisher in the United States, where we estimated demand elasticities for various books. We are fitting it in Stan. And that's that. So that's the plan. Hope that's okay with everything. So why do we bother with Bayesian approach? For me, and I think for people that work in Bayesian inference, it's a way to express our beliefs, right? There's no such thing as objectivity, right? Like you have to sort of admit that we all have opinions. Some are more informed than the other. We'd like to be able to express those opinions. And Bayesian approach allows us to express an opinion. Whether that opinion is a choice of the likelihood function or the prior or whatever, those are all beliefs that we express. And then we spend a lot of time checking if our assumptions are correct. We also want to be able to estimate uncertainty, and we want to estimate uncertainty well. And Bayesian is really the only way to get a full picture of the uncertainty and the true picture of the uncertainty. We also like to fit big models. I'll talk about the big models a bit more, in a sense that we want to be able to express all the structure that is in the data. Those models, sometimes called multi-level or hierarchical, and the only way really to fit them fully is to use Bayesian approach. There's no really other way. And another reason, which is often overlooked, is that we want to be able to deal with small data. Everybody talks about big data, but small data is something that is really important because at the level of the observation, at the unit of measurement that you care about, like maybe a customer making purchases for a specific product, even though the whole data set is enormous for that particular unit, we may only have a few data points. But we still want to make inference level, right? So we need a strong model. But of course, you come to a machine learning meetup and everybody says, well, what about big data? You know, if you run this thing on Hadoop or Spark or whatever the latest thing is, the answer is no. But we don't really have to. And to demonstrate, I stole this diagram from my colleague there, Mr. Michael, is one of the stand developers. And so think about this thing, the space of size of data and model complexity. By model complexity, we mean essentially two things. We mean the complexity of the likelihood function and the number of parameters that are expressed in the model, right? And so generally speaking, what happens is in big data today is that you have people like when they run things on Hadoop, for instance, they'll fit like 1 million small models in like subsystems of the data. And so you have like this huge data set, but the models are really simple. A lot of things, when models get complex, they can only be fit on small data. We're actually trying to push this curve out to the right? And to fit big models and big data, you need tools that scale well with the number of parameters that you're trying to estimate. And so I won't tell you that Stan can fit these huge data models, right? That we're still not quite there yet, but it can handle pretty large data sets already. And we have fit, and people have fit models that have millions of parameters. Okay, so that's pretty impressive. Okay, so another point, I guess, a contrast with the traditional machine learning and Bayesian approach is that it's a bit more subtle, and that is this idea of a model, and a particular causal model. You could do like a very long talk on causal models. I'm not going to do that, but I just want to give you a flavor for a situation where you may want to have one. And so, say we have this problem, which I'll show you through the model for a bit later. But we have a large retailer, and we want to do some prediction, maybe, right? And so we have one problem, A, which is that we want to know how many units of each product will be sold, say tomorrow, given everything that we have observed of these products up to today. And the second problem is the same retailer wants to find a revenue maximizing price. They want to be able to find the price which maximizes it. And so what we observe are these quantities sold of each product over time, metadata, and so on. And so which one of these is a purely predictive model? Anybody? A, right? Yeah. I'm just, and so for these class of models, I can actually throw a lot of covariates into like a big box, like a neural network or something else. It'll give me a prediction. That might be good. For this kind of thing, there's really almost no chance of you getting a good prediction for a model where you like throw all the covariates into the box, right? Because what we're asking here is fundamentally a question of not what the quantity is going to be tomorrow. We're asking, given our model, right, if I were to change price, what would be the expected change in quantity sold? I'm asking a model for a counterfactual. And in order for my model to give me honest answers, it has to be able to isolate that effect, right? And so I need to express that model. I can't just throw this stuff into the black box. And you know, economists, for that reason, economists they don't actually do machine learning. They don't necessarily do Bayesian, but they do create models that are of causal variety. And my claim is that you actually should be using Bayesian models for that as well. Okay, so why Stan? Before I say why Stan, maybe I should say what the hell is Stan, right? So I don't know if you, how many here are actually from seen Stan, or maybe you've written the Stan program or know what Stan is? Anybody? Okay, so much smaller group. Okay, so Stan is what we call a probabilistic programming language. It's an imperative probabilistic programming language where what we do is we actually write down the likelihood. This is the part of the model that gives rise to the data, or we believe gives rise to the data, and the prior information about the parameters. So that's one thing. It also has this C++ math SAS library. It implements really fast algorithm called auto differentiation, which is actually auto diff is what you want to do, whether you're doing like Stan or not. You never want to compute these like finite differences to estimate like gradients or anything like that. Today, you really should be using auto diff. Stan probably has one of the fastest implementations of those. And there's an algorithm toolbox with that. So the inference algorithms are separate from the model, right? Unlike inside of a neural net or something like that, where the inference algorithm and the model are kind of in the same place and hidden. The model here is exposed, but the inference algorithm is what does like the really hard work of trying to estimate the distribution of parameters. And so in that case, it was built mostly for doing full Bayesian inference, which means that you get back the posterior distribution. But it also has some other algorithms built in, like approximate Bayes. Maybe you heard a thing called variational inference that tries to find like an approximate, tries to match a posterior with like some Bayes distributions. It's there. You can also do optimization. But all those things are sort of like nice to have. We really are interested in the full Bayesian inference algorithm. And it's pretty young. Like Stan was, only a few years old, 2011. There are a bunch of interfaces to all kinds of languages out there. Since it's own programming language, you actually don't have to use it an interface. You can just have Stan programs. And so people who deploy it in like production for doing auto model building or something like this, they tend to just use this thing we call command Stan. That can run, usually runs on Linux, but it'll run on other things as well. So if you're doing like exploratory kind of stuff and model building, R is probably the most developed interface, but there are also Julia, MATLAB, Stata. Somebody just did a Mathematica interface as well. Okay, then there are some tools that we've developed for model evaluation and model critique. This is the part. We spend a lot of time in this area, and so it's important to have some tools for that. So who are the users? Stan is an open source project. The command Stan is licensed under a very, very permissive open source license called BSD. It's the kind of license that anybody can use. Nobody has to tell us. People can like embed it into their own products, sell them, and that's totally cool. So we don't really know, but we have I think we just had the 2,000 registered on the user mailing list recently. We get over 10,000 manual downloads when there's new release, and it's been used for pretty complex models. So like people that do climate science, drug trials, population dynamics, you can read this. I mean, pretty much everywhere we've heard of Stan. These are some of the people in the industry that are using Stan today. As I mentioned, what are some of the main difference between Stan and traditional machine learning has to do with the fact that we express the model directly, right? So to make it somewhat concrete, if you look at this side here in traditional machine learning, maybe you run a neural net, you give it some data, you put some meta parameters for the algorithm, and it spits out some predictions. In Stan, you actually have to write the model, right? So there's like a model block in the Stan language where this one says, okay, my model follows a normal likelihood with this mean. This can be as complex as you want, as an example. So when Stan finishes, assuming that you didn't supply these 3 parameters as data, it will give you distributions for these alpha, beta, and so that's what we get at. And if, from that point you want to use an estimate, sure, go ahead. But we tend to work with a full distribution, predictive distribution. I'll tell you about it in a minute. And it's particularly important for decision theoretic things. And the decision theoretic is maybe like an academic term, but anytime you need to make a decision where you want to incorporate uncertainty, the Bayesian approach is really what you want to use because it's the only right estimate of your uncertainty. You can't really get uncertainty estimates from these types of tools. They sometimes report them, but they're often used on assumptions that require enormous amount of data that usually do not exist. So for decision making, for like big decisions, you really need to go to a Bayesian model.
How many people do this?
So Stein does not come with pre-installed models. You're right. It's a language for specifying a model. So a model. So unlike, let's say, like an R package, an R software where you call LM, to fit a linear model, there's no LM that you can call and scan. You have to write this thing, and it'll give you a much better answer than LM would. But also, you can immediately say, well, I don't think my errors are normal, right? So you can, instead of normal, you can say like student P or something, and that becomes like a robust regression, and so on and so forth, right? You have to write the model. That's the price you pay. The price you pay up front, right? Okay, so I hope I convinced you that the Bayesian approach is a good approach for the kinds of things that require uncertainty, which is mostly. But there are other algorithms that's been around for many years that are also based on Markov chain Monte Carlo. For those of you, a lot of you raised your hand when I asked about a Bayesian thing. You must have heard about things like Metropolis or Endomorph Metropolis algorithm. It was one of the first ones that was invented, and a Gibbs algorithm, which is implemented in a program called Bugs, right? And all these sort of variations of the Bugs program. And so I won't go into too much detail for like how scan is different, but to give you a picture of the kind of exploration you get from scan, here we call this nuts algorithm, versus these other tools, right? So this is simulated data on an ill-conditioned 250-dimensional multivariate normal, right, with high correlation structure inside, right? And it's projected onto two-dimensional space, and that's the projections that you see. So we know this model, we can draw independent samples. So this is a comparison plot, right? This is what the independent draws look like. Here's what a Metropolis exploration gives you after 1 million samples, right? So it will take quite a long time. And in 1 million samples from Gibbs will give you something like this. That maybe got sort of the middle, but completely missed the lower tail, right? And then you go there. And if you look at nuts, only after 1,000 samples, right, we get almost exactly to this search. And so the beauty of HNC and nuts and algorithms that are built into scan is that it scales really well as parameter space expands to very large numbers. And those are the kind of models that we see today, and those are the kind of models that we pick. And this is why we are all so excited about scan. This is why I quit my job recently and decided to do this thing. Just as a picture of a Hamiltonian system, which this is kind of a simulation where we're trying to do an exploration of this this is like a two-dimensional normal. And the thing to pay attention to is like the step size. This algorithm that is being used based on this physical model of Hamiltonian dynamics, has some sensitivity to these tuning parameters, as a lot of these step sizes are. So this is like a very small step size. You see, it's exploring like the middle of the range, and then this is the large step size that sort of goes out of bounds, and then this one is sort of just right. So one of the innovations that came out of the research that I think that originally was done by Andrew Gellman and Matt Hoffman at Princeton was to figure out like how to self-tune this system, right? So it was very, very sensitive to tuning it. So this is what was implemented instead. This is why it works really, really well without too much input. Okay, so let me move on to the setup that we will now use to build up a model, and I'll show you like a more of a stand model in what it does. But I'll be remiss not to mention the kind of things that we tend to do when we work with data. And I highlighted the parts that are usually different from what I see like a typical data scientist do, right? And so that's the reason I sort of like put these in yellow, right? And so the first thing that we tend to do when we try and start analysis, we don't like download a huge data set and start like plotting all the correlations and looking for patterns and stuff. We tend not to do that. We tend to gather a lot of prior knowledge, and we'd like to write down the simplest plausible data generating process, right? The simplest plausible likelihood for these data that we might have observed. We call these models generative models because we could, since we can write them down, we can simulate from these models, right? And so the very first thing we do is we write it down, we simulate some data, and we try to recover the parameters so that to give ourselves a bit of comfort that we could, in this very laboratory environment, know what we're doing, right? It's very easy to make a mistake. We don't, just develop this big model and like let it rip on this big data set. There's sort of no chance. So that's a part of the workflow. Only then do we fit it on real data. And we spend a ton of time in this evaluation and criticize model step. We look at how this model performs in different conditions. We look at how it does for different types of covariates. The model may be weak in some places. No models are perfect, but we want to know where it's weak, right? If I'm going to use a model, for instance, for this problem of estimating demand elasticities, if my model doesn't give me good predictions for high volume, let's say titles that sell like thousands of units a week or something, I really want to know that. I may still use the model for low volume stuff where it does really well. So the point is, like, we really want to like beat the crap out of our models to understand where they're weak, because we know they're weak somewhere, and we don't want to go full. So this good enough thing is a very there's like no guarantees that it may be good enough for someone. There's some kinds of things that we know are just wrong, but in general, like, this does come down to a decision on the part of the person who's doing the evaluation. And so I'll show you one of the ways which we do it. We do it with some graphical checks. Okay, and then we build the model up, right? We start adding structure. We see if we get improvement or we adding noise or whatever. That's so since you guys are expert Bayesians, you don't need to see this, but for those of you born, Bayesian machinery itself is really simple. The complication is not in this, it's in how to get samples. But I'm sure, have seen this. You can write the joint probability in these two different ways because you can permute these guys. And so if you make them equal to one another, you can express this posterior parameter theta given y. We call it y is always data. Data are not like covariates. Data are what we call the things that were modeled, like the quantity sold or like the health of the patient. It's the stuff that goes to the left tilde. Okay. And so in this final form, we generally call their names for the different parts of this thing. So this is what we call the likelihood function. In the choice of the likelihood here, we don't differ from frequentist. They work with some likelihood. We're not trying to maximize this. We're not trying to find some top of the hill thing. Then we specify some prior distribution and this thing sometimes for marginal length. But essentially, we mostly use this thing that doesn't depend on theta, that gets integrated out. And so we generally care mostly about this numerator, right? That's where they do. Okay, so what does that look like? So in a very, very simple thing, suppose we have a coin flipping or Bernoulli model. You, I'm sure, would agree that this part here would be the likelihood for one observation. We take them as independent. We take the product of them. That's the likelihood thing, which we could write this way. And then, well, we can ask, oh, what happens to the prior? You promised us the prior. So let's say the prior is flat, is uniform, so it has a contribution of 1 on the raw scale and 0 on the large scale. So we'll ignore it for now. But like this thing, it would, if we take the logarithm of this, the sums come down, like it sort of looks like that. So this is like from an introductory probability class, you should probably see this. So we can just write this thing, you know, for unidimensional theta, for one-dimensional parameter, you don't need a fancy machinery. You could just do a grid and it'll be fine. And so, you know, if we set up some data, 5 data points, and we'll write this as our syntax. And so I just want you to agree with me that this for loop is just these two sums, right? That's all we do. When we say, we sometimes say like the points, every point contributes to the likelihood, that's what we need. So we go through every point supply here from the data that's passed in, and then we add up the slug photo. Okay. You know, don't do this, but like these are the way it's written. It's like arithmetically unstable, and so I'm not showing you how to do it. I want to just demonstrate a point. This, you know, we can, if you don't like to write things from scratch, you can do the same thing with p binom and r, and here we get the same results to when we evaluate this log photo. That's another good idea, to have 2 ways of doing stuff, so we don't. Okay, and so I promised you that we don't need any fancy machinery, so we can just generate a grid of theta. We can compute this posterior. Go back. It was in log scale, so it'll exponentiate it, and so on and so forth. And then I could just sample in proportion to the posterior probability. So that the magic of Stan happens because this line here is impossible to do when theta gets very, very high dimension. If it were easy to do that, there would be no need for MCMC or any of those tools. All the hard work happens here. But you know, here we're in this sort of an easy case. We can compute the maximum likelihood estimate, and so we can draw the posterior probability of theta here and compare the maximum MLE. Looks fine. Okay, so the same thing you can write down in Stan. So this is a Stan program, maybe one of the simpler ones. And those are like the 3 parts of the Stan program that should be present in all Stan programs. Data is the stuff that you know, right? These are the knowns, you pass them in. Here we know the number of points that we know, you know, these zeros and ones that come in. Theta is what we're trying to estimate. I haven't put any priors here. That's a bad idea. But I kind of wanted you to see that there's still direct mapping, right? Target is a reserved word and scan. That's the shorthand for that log probability. That's what we're accumulating. Okay, so same thing as we did in R. Same, translates to this, and don't do it. Okay. Why I don't do it is just do this. Right? So there are distributions that are built scan. They typically very, very fast. They work well. And so like this whole mess. This is also arithmetically unstable. All those other things. This will work fine. Okay, so you can usually express your whole model without bothering with this notation where you have to manually increment the log probability. You can usually just work with these local distributions. Not always. And sometimes we do this, but like there's quite a rich collection here that we could draw. Okay. Any questions so far? Is that okay? Everybody's on. So I'm going to tell you now about this kind of a real industrial case where you have a publisher and they have thousands and thousands of books in their catalogs. They sell them through in the U.S. like most merchandise entities is sold through Amazon.com. Right? I think you don't have much Amazon in France, yes?
Yeah, we do.
You do?
Yeah.
Is there a lot of like books are being sold through Amazon?
I think so.
Yeah.
It's one of the contentious issues.
Yeah. Okay. I heard there's like price. They have to price them.
Yes, they have to conform to.
They have to conform to
laws.
local pricing. Yeah, that's good because in the U.S. they're like killing all of the local retailers. But anyway, that's a different story. I have a lot of Amazon stories. They essentially like this book publisher, most of the inventory goes sold through that. And so they actually don't know who buys their books. That's not right. Like a retailer knows, but of course a retailer is very secretive about their customers. So they have all these books. They have like new authors that come on all the time. They're authors that have series of books that are published that behave different from like regular books. There are a lot of like complexity, seasonality. And so the question that this publisher is asking is probably what most people who sell stuff are asking, which is what is the right price, right? And I alluded to this earlier when I asked you the kind of type of model that you would need to answer that question. And the reason I sort of introduced it is because with this experience with the publisher and the fact that we really have to think very carefully about isolating the effect of price on the sales. It's not enough to get a prediction. It's just not enough. It's not sufficient. So I'll show you like a sort of a very simple base model that we started with, from which we started to build up over time. And we always start, right, like we always start simple. So the simplest thing was that, well, suppose I only have one product, right? I don't have many products, I just sell one product. And I want to know, like, what are the important things that affect the price of that product? I'm not an economist, but I consult with one, and I'll talk to people who've been working in that business for a long time. So those people tell me, well, the age of the product is a very important contributor. So it tends to be priced. It tends to sell a lot of quantity at the beginning, whether maybe they launch it, and there's like corresponding promotional activities and so on, and then there's some kind of decay. So over time. So we'll say, okay, so we'll say the quantity is some function of this term of product age and the price of the book. And we also allow for some departures from linearity to include the square term price. Economists do this stuff a lot. there's not the only way to model this kind of thing. There are other things we could do, but for now, let's just leave it at that. And so I would say, okay, so I'm going to just start with it that single product, and I'm going to say that it's for product I, my quantity is normal x beta, which xi are these things. So with some variance. Okay. Now, the kind of model I worked with first was the model that sold very few units. So you actually, this kind of model, I know it's not going to work for it, right? Because there are like zeros there. There's something called there's an over dispersion that happens, and so you actually need a count model, right? A model that allows for that kind of thing. When we deal with count models, we usually fit something called a negative binomial, which, if you're not so familiar with that, it's like a Poisson model where we do not force the mean to be equal to the variance, right, which is the basic assumption in Poisson, which is very unrealistic, right? So the variance is still constrained, but it's allowed to vary up to this, the proportion of the square of the mean, right? And so this is the setup. This model is parameterized by mu p, where mu is this exponential function of the this x beta. Okay, so the very first thing I do, I simulate, right? I simulate a data that I think is consistent with this process, right? And so I write some R code that, that has some kind of a known intercepts and known theta. This is the over dispersion parameter. I get this kind of picture. It's okay, that's nice. So now, I can do that for many products. So we have some code that we've written to to simulate, many products that would have this kind of relationship. You can see I can sort of simulate the normal process, so negative binomial. Anybody could do it. It's pretty easy to do an R, right? Just this whole thing. Okay, but what about the real data? So then, okay, I can take a look at the real data, and I could look at it and say, well, does it look like what I've simulated? I don't know. I mean, yeah, this thing maybe. Others probably not. So I know this model is probably not going to be that great, but that's okay. I'm not going to bank on it, but it's okay. I can start fitting it and seeing what it would give me. And so here's like a more realistic. I showed you like a super toy model instead. So this is maybe a little bit more realistic model that encodes this negative binomial likelihood for one product. This is still you just using one product, right? And so here we're adding some parameters, right? There's a mean parameter. There's this time coefficient, right? We're fitting the product age, and this dispersion parameter, and that's these are specified in this plot, and then the model contains what we call the linear predictors to the function for mean, right? This is our intercept times theta, and we specify the priors for the coefficients. A lot could be said about this. I'm not going to tell you a story about priors. There are some guidelines. Some of the best ones are actually on if you go to Stan's GitHub account, there's like a wiki page that writes out like recommendations for what priors to use if you're like completely new. One thing I'll say is that if you are a bugs user and you're coming to Stan, please go read that first, because the kind of priors you would use are just going to be not great. You have to do them in bugs for reasons that I won't go into that you really don't need to do. In Stan, and we spend a lot of time, like Stan developers, answering questions in user lists why you shouldn't do it. So yeah, if you're coming from bugs, don't parameterize your models the way you would in bugs. Just go look at that wiki for some guidance. But okay, so I just fit this model, right? Like this is our syntax. We put stand programs such as this in a separate file. It's just a text file. We give it the data. We pass that in. These are some control parameters for the sampler. Typically, another thing people do when they come for bugs, they set the iterations to like 100,000 or something. We rarely see iterations greater than like 1,000 or 2,000 or something like that. For a model like this, a few hundred iterations would be enough to fit it. So this is usually a smaller number which you expect. And once I fit this model, this process completes, I extract the draws. So remember, I now get back the draws, posterior draws for each of the parameters, the full posterior. I don't get some summaries. I can compute summary statistics on it. I get back the draws, and then I could compute the quantiles. And so if you recall, when we simulated the data, my mean was like around 85, beta was minus 0.10, and 5 was standard. So here's where I check. Did I capture it? Did I get them back? And they're all covered. So at least that tells me that, okay, I know that I'm getting the right things out of the things that I can control. Right? This gives me some indication that the model is doing what I think it's doing. And so there are other things that you would do, such as looking at some diagnostics. You have to look at some diagnostics for the markup chains themselves. You can look at posterior draws. There's some nice helper functions that are available in R. If you're inside of R, you can just give it a fitted object, like, and put it to this pairs function, like R pairs function. It'll display the parameters. You can look for, see if these correlations make sense. If there are problems, sometimes they'll be evident here on these plots. There's also, I mentioned, there's like a tool for exploring the whole fitted object. It's called Shiny Stand. There's an R package for that. This is where we actually look at the draws. These are the core of the markup chains. We want to see them like nicely intertwined and mixed and sort of like random. Right? We don't want to see patterns. We don't want to see them diverging. We want to see what's called good mixing. And we can also look at like a full distribution of this alpha parameter that we estimated and others as well. So it's kind of nice for estimating, for evaluating the model. Okay. So now you're saying, well, that's very nice and well, but like we don't have one product, right? I have like a lot of products. And this is where we really get into the benefit of the Bayesian approach, because I can fit a hierarchical model now. I can instead of fitting a separate model to each product, I want to get something that's called pooling effects. In other words, I want to be able to use information at different levels of hierarchy to inform the sort of the lower levels. So, because like for some products, maybe I'm only observing a few data points, right? And so I cannot make inferences there unless I use that information. And so pooling is something that confuses people, I think, and maybe turns them off of this Bayesian thing. But conceptually, it's pretty simple. And to sort of demonstrate that, here's like a formula that I think develops a bit of intuition of how pooling works. So say if we didn't have any covariates, all I wanted to do is estimate the average sales for each book in the catalog. Right? That's all I wanted to do. And so we'll call this alpha hat J, where J is indexes every book. And so this pooled estimate, it could be expressed in this way, which is to say that it's these weighted averages between this number of observations that I have for that book J divided by the within book variance, right, times the average sales for book J, plus the inverse of the variance among sales, average sales of different books, times the average sales across all books. Okay, so to disentangle that a bit, look at two extreme cases. Suppose I have, for book J, I have no observations at all, right? So when NJ goes to 0, you see that these disappear. Okay, this also cancels. And so if I don't have any observations for that book, my average sale for that book is just an overall average. You see that? On the other extreme case, if NJ goes to infinity, if I have infinite data, then these terms sort of disappear, right? They get dominated by this term here, and then my estimate of these of the sale for this book J is just this term here, which is the average sales for this particular book. So you see the trade-off now, and in between, right, it's going to be making these trade-offs to the amount of data that I have in there. So that is certainly like the idea behind how it fully works. Now, you can specify these models in STAN pretty easily. When people are getting started and they're a little bit maybe afraid to write STAN code, which they shouldn't be, but sometimes they are. And so a couple of developers of STAN made a package where you can estimate these kinds of models without writing STAN code. That package is called RSTAN-ARM. And if you've used a R package called Elmer, how many heard of LMER? Okay, some of you. So Elmer was the package that everybody went to estimate mixed, what they call mixed effects models, right? The models where you can fit these hierarchical structures. They only support kind of a limited number of them, and obviously you can only estimate the kind of models they encoded, but it was quite popular nonetheless. It's still being used. And it has this sort of flexible syntax where you could specify your the fixed, what they call fixed and random effects, with like an R formula in it. Okay. And so if we wanted to fit a model like this, and by this I mean the kind of model you saw in STAN, only you wanted to fit it for like many books at the same time, you wanted to do it hierarchically, you could just write it in this formula interface once you have this RSTAN-ARM package by calling this stanglimmer.nv and supplying this kind of formula to the algorithm. The algorithm sampling just means to fit it with full base. That's the default anyway. You can use that. And this will start sampling right away. So they've compiled a whole bunch of models. And so the gentleman who asked earlier what type of models were built in, well, none are built into STAN, but a bunch are built into RSTAN-ARM. And so if you're curious, you can like Google RSTAN-ARM. You'll see the CRAN page for it, and you'll see the description of models that basically like all the GLMs have been encoded, and some others as well, and they also can be done hierarchically, which is a big thing. This is really, if you're doing Elmer today, you really should be like switching to RSTAN. Okay, so you fit your model, you have your posterior draws, and you're ready to make decisions, right? Wrong. You're not ready to make decisions at all because we don't really know how well the model works, right? And to know how well the model works, we need this quantity, right? We call this a posterior predicted distribution. And if the way you read this integral is essentially, okay, so we have this quantity here, we have the posterior. So we take the likelihood function that we already specified, so we know it, over the parameter theta, right, that we estimated, evaluate it as the new data, right, or maybe it's existing data, but let's say it's some kind of new data, and we weight that by this posterior distribution. So it's a kind of a weighted average that we take over the entire theta, right? And when you do that, you know, the theta thing comes out, and then you get this distributed distribution of the new data given the data that we have estimated in the model. Now, the nice thing about this quantity is that it takes into account all of the uncertainty, right? It takes into account all the uncertainty in the model and parameters, and it's sort of the best thing that we can do to understand the variability in you know. So that's the kind of thing that we want, and so it's quite easy to get out of STAN. But for instance, when I fit this model that I showed you on the other page, and if you do it in our state arm, there's like a few convenient functions that have been implemented to do this model checking. So we call this posterior predictive checks, and that's how this thing is read, PPF check. And if I were to run this on this model, it would produce a picture that looks something like this, right? And so these are the y's, right? These are the observed y's, right? I'm looking at the y's that have actually, these are quantities, okay? And then the black lines are the simulations from my model, given my estimates. I can draw a lot of them, and so I can get a sense for how well my data that I've seen represents reality. So what does this picture show us? I mean, for the most part, the things that are selling some lower quantity of product seem to be fitting pretty well. But once they go out on the tail in the larger quantities, it doesn't really look so good, right? I'm not doing so great. Like here, I'm still sort of capturing something, but once I go to like this 2000 thing, it doesn't look so great. So that's a nice thing for me to know. Like, first of all, this model is not good enough, but I also know sort of where it may not be good enough. Right? So it helps me now investigate it further, and so on. The other thing that we want to check, which is very easy to do for Bayesian models, is we want to check the model calibration. So if you are not a Bayesian, you may have not even tried or know what that's supposed to mean. But calibration just means that, like, you know, if we're making predictions for, and we are drawing the 50% credible intervals, we want to see the observations there 50% of the time, right? Then we are well calibrated. So I can run some functions to check these calibration statistics, and I want to make sure that like I'm well calibrated. Now, even if I'm well calibrated, right, it doesn't mean I have good predictions. So it's still sort of not enough, because you can imagine a well calibrated model that has very wide uncertainties, right? They're sort of not good enough. But again, I can measure these, like all these things I can measure, right? And that's sort of the point I'm trying to make. But like a combination of these posterior prediction checks, calibration checks, and so on, they sort of add to our knowledge about the goodness of this model. So, you know, to show you maybe some of the predictions, you know, I have to take out because this is real data, so I can't show you the axes. But these are like actual product sales. The x-axis is time, and the y are quantity sold, and the color are the changes in price. So I can, like, for instance, I can see here that the price was dropped. You know, it was like somewhere around like $12, and it went to 5 right around here, and then, you know, we predicted this increase. Similar here, we predicted this increase. The shaded areas are the credible intervals. I think these are 50%. Right, but we can sort of look at it by product, and see how well we're doing. But this is not what we wanted, right? I want a prediction I want to find out the optimal price. I don't just want a prediction for the price we observe, right? So there's an additional step that I want to do now, but that's also easy, relatively speaking, because all I do is I say, okay, you know, my model has these price terms. So I'm saying, okay, model, I'm going to give you now a grid of these prices that I know are like a reasonable set of values where each of the products may be priced at. And so I give it that grid, and then I ask the model to generate the predictions for me for each one of these price points, for each one of these products. And now I can take a look at these demand elasticities. So this picture on the left here are for each one product. I have a predicted quantity sold at different price. So this is as an increasing function of price. So the first thing I want to check is I want to make sure these are in fact downward sloping, right? Why? Because like this is not a luxury good. We don't see upward sloping demand curves there, and so I kind of want to make sure that like these are sort of the right shape. But I'm also very much interested in the uncertainty that we got at different price points. And as you can see, those uncertainties are not uniform. We estimate some of them better than others. And so when it comes time to make an actual decision about which price to go to, I may want to take that uncertainty and estimation into account, right? Because a publishing house executive may have a different utility function from me or from my friend about how much he's willing to pay for an additional unit of uncertainty, right? It's not just a maximum of some thing, right? It's also, and so like this can then be translated into the revenue curves, right? So because these are quantities, I can now multiply those times price, I can get the revenue curve, and then we can reason about the kind of utility function that we want to apply, whether it's the maximum revenue or do we maybe want to penalize some of these points in the curve for the uncertainty that is inherent in our estimate. Okay. That kind of thing, I hope I've convinced you, is only available to you if we have these uncertainties estimated correctly. And so that's the end of my talk. If you want to learn more or you want to start learning about the hierarchical models, for me, this book was the most informative and perhaps the more introductory in nature. It's Andrew wrote it in Jennifer Hill. There's going to be an update to that coming out sometime. I don't know when, but there will be. But this one uses Elmer, and it uses plugs because at the time there was no Stan. But a lot of the models have been ported to Stan, and they're available in our example model repository. This is a recent book that came out, which I have a copy and it's pretty good. People who read it say it's quite good. If you're new to Bayesian, you know, I think Richard did a good job in statistical rethinking in that he sort of starts from the first principles. Like he doesn't do the same thing that you would get if you take like a statistical inference class at a traditional university. Well, they'll teach you about like Neiman Pearson and like maximum likelihood estimation, all that stuff. He actually built up the Bayesian approach from the like probability upward, and he didn't spend time on things that are unnecessary, so too technical. So you have to do some coding and a little bit of math, but not bad. This one is not a very technical book either, Bayesian data analysis, but it does assume that you know a lot. So it just makes a lot of assumptions. So if you're like new to Bayesian, this may be a different vision. If you're not, this is great reference as well. You have a copy of these. Well, I think the presentation, you don't need to write this down, but there are a bunch of papers now on Stan, some introductory papers. This one, of course, with your, it's more of like a statistician's view. This second one, Bob Carpenter wrote, it's more like a computer scientist view. I really like Michael's Hamiltonian Monte Carlo YouTube videos. So like if you want to know how like an intuition behind how a Hamiltonian Monte Carlo works, just go to YouTube and type in Hamiltonian Monte Carlos, and it'll pop up. Tons more stuff available on mcstan.org, so you can go there and check that out. So that's me doing a post in the Rodin Museum, and I think if Rodin were alive, he probably wouldn't hire me.
That's great fiction.
Yeah. So yeah. You know, if you this is like not for kids. This is Twitter, you know, so for adults only. Feel free to send me an email. We do STAN classes. We do some commercial support work with STAN as well. Or if you just want to talk about STAN, send me an email. And that's it. Thank you very much. Nice to meet you.
Great, thank you very much. We're going to have time from Eric coming forward, and we'll have a panel discussion soon. So we're going to ask all the questions to Eric and the developers. The developers are here to talk. And then we'll have food and beer.
Okay, I'll keep this short because I know everyone's kind of hungry and thirsty right now, but my name's Eric. I'm a data scientist here at DataCoo. Just by show of hands, how many of you guys have been here before or heard of DataCoo? Okay, cool, most people. All right. Anyways, who are we? I just have one slide about us. So we're about 60 people here in our Paris office, some data engineers, data scientists, data geeks in general. We have about 100 clients in Paris. Some of our bigger names are L'Oreal and BlaBlaCar. In the US, people like Pfizer and Thomson Reuters. We have two main offices here. This is our headquarters. Our other larger office is in New York. We also have a presence in London and in San Francisco. We only make one product. Officially, it's called DataCoo DSS. And today I'm talking about how you can use that product with Stan, which we just heard about. I'm going to present my own data science workflow, similar to what was presented earlier. Again, I think you guys have seen something like this a lot. Data science look like in practice? Well, you got to get your data here. You got to prepare it. You got to clean it, filter it, visualize it. Then when you're happy with it, you make your model, you evaluate it. Again, building that model and evaluating it is a critical part, but also you have to think about acquiring and preparing it. Anyways, you go around the circle until you're happy with it. Then when you're happy with your model, you put it into production. Maybe you use it every day. Maybe you send those predictions to a client, whatever you have. So how did DSS and Stan work together? Stan is excellent for model creation and evaluating your model. So Stan you can really use for those two halves of the circle. DSS, what is it really good for? It's really good for getting your data, cleaning it, exploring it, and we can also help out here with the deployment. All right, does that make sense? So Stan really good with model creation and evaluation. DataCoo, we're really good with acquiring the data, preparing the data, and then deploying your final model. Here at this other end, this is you guys. So your business, your scientific understanding of your problem, your data, that's what's going to be used at the beginning part. Cool. Any questions on that?
Yeah, actually.
Yeah.
What language is it to, like, what's the backend?
Oh, okay. So I'll show you in a second what it is. So we support a bunch of different languages. So R, Python, Bash, SQL, Scala.
Okay, so what's the backend? What's the active backend?
Oh, the backend. So for the machine learning, it's written in Python. The backend's written in Java. Of course, the front is written in JavaScript. Yeah.
Yeah. Well, when you say deployments, production,
Yes. Yeah. And so when we say to production, we mean deploying. Yeah. So Hadoop is a bit tricky. So of course, if you train a model, we can in something like MLlib, we can deploy that on top of Hadoop. If you train it with something else, we can deploy that on top of Hadoop. Yeah, in production, something turning over every day, every week, or even turning it into a real-time model. Your data's coming in real time and stored in real time. So, yeah, I can show you. I'll show you a demo in a second. Yeah. Did not expect so many questions so early. Anyone have any other questions?
Well, they're not that hungry.
Exactly. They keep asking, but it's super hungry. Okay, so today's demo. Okay, what are we going to work with? We're doing topic modeling of Twitter. So we're using Twitter, DataCoo, obviously, and Sand, obviously. So DataCoo, we're kind of Twitter, taking in the tweets, cleaning the tweets, filtering them, and then we're passing them into Sand for doing some topic modeling. So today, yeah, we're doing topic modeling on Twitter. Before we actually get into DSS, I wanted to talk a bit about topic modeling. So show of hands, how many people are familiar with topic modeling? Cool. So maybe 30% of people. How many people are familiar with clustering in general? Clustering, okay, cool. So topic modeling is closely related to clustering. It's sort of like, in my mind, clustering for NLP stuff. All right, so this is my really high-level way of explaining topic modeling. So the way topic modeling works, at least for me, maybe people with more experience will disagree with me, you have three different things. So one, you have your documents, then you have a set of topics. So I'm just going to say Twitter, there's news on Twitter, there's pop culture stuff, and then you have marketing stuff, right? Then the tweets are composed of words, so just 5 sample words in this vocabulary. So product, report, award, Trump, and video. So we'll say high-level stuff. So a document, let's say it was about news. So that document is assigned to a topic. Once you have the topic, you know then what words are going to be in the document. So news, that's going to be something about maybe Trump. It's going to be about reports. Okay, maybe not the word report, a new report on Trump, something like that.
You're being reported.
Yeah, exactly. Something about pop culture, maybe we had a tweet and it's about pop culture. It's going to include words like video, awards, maybe MTV Music Video Awards. That'd be something about pop culture. Similarly, maybe something from a marketing department. That document's going to have something talking about a product, or maybe a video about a product, those sorts of things. That's a super high-level overview of topic modeling. Do documents, they're assigned to topics. Based on the topics, you know the words. But we're all Bayesians here, at least for tonight. So Bayesians don't like viewing things in terms of rigid estimates. So Bayesian topic modeling would say, okay, here's a tweet. I think maybe there's a 20% chance it's about the news, a 70% chance it's about pop culture, and a 10% chance it's about marketing. Right, does that make sense? So rather than specifying this document is this topic, you get a distribution. Questions on that? Good. All right. Then if it's about pop culture, we say, okay, maybe tweets about pop culture. There's a 40% chance it contains the word video, 40% the word award, maybe 10% Trump, 5% report, 5% product.
Yeah, I'm sorry, this means that the probabilities are in check, right?
Yeah.
But you just told that it's possible to have multiple words, like probably multiple keywords.
Yeah, and so then basically, yeah, so for instance, for each topic, you'll have a distribution for all of your words. So for instance, this news here will also have a distribution for all of the possible words, right? And so then basically, to do the Bayesian thing here, you take, okay, there's a 70% chance it's in pop culture, that 70% chance times the 40% for the award, and you get to start unraveling the hierarchy. Does that make sense? Yeah. Okay. I was hoping somebody wouldn't have asked that. Yeah, okay. Anyway, so I can show you the stand code in the project. There's a lot of different ways of doing it. This is using something called a latent Dirichlet allocation, right? So it's assuming these are drawn from a multinomial distribution. The prior on that is a Dirichlet distribution. So both for the topics and the words, that's how it works. Any other questions? Yeah, and then you can get more complicated than that. All right. Okay, bad news though, the topics, they're hidden. So you don't know a priori what the topics are about. So what's going to happen is you're going to put your data into the model. It's going to say, okay, I'm looking for 3 different topics. And then it'll tell you, okay, for topic 2, it's talking about awards and videos. So then it's up to us as the end user to infer, okay, topic 2, that's about pop culture. Topic 1, that one is about news. Okay, makes sense? The topics are hidden. We don't know what they are a priori. We don't have a label. We have to infer that ourselves. Okay. All right, so again, high-level overview. You get your documents. You put them into this algorithm. You get 2 outputs. One is for each topic. Sorry, for each document, how probable are each of the topics. The second output is for each topic, how probable are each of the words. Okay, so you map your documents on the topics, you map your topics on the words. Yeah, anyway, so for this, we're using tweets, and then the algorithm is LDA, is what I'm using right here. All right. Any other questions before we go on? People are getting hungry. Anyways, all right, so workflow again. All right, we have data acquisition, data prep, model creation, evaluation, and then deployment are these 5 steps. So I'm about to go into DSS in a second here, but this is what the overall workflow is. Have any of you guys, how many of you guys have seen our product before? Okay. Yeah, just a quick overview. Basically, each of these blue squares is a data set. Each of the circles is a computational step. The circles can be done in a visual interface, which are the yellow ones. They can also be done in code, which is what the red ones are. So you'll see some red. All right, so the first part of this, what we call flow, so it's a directed graph of data sets. This all the way up until here. This is data cleaning and data preparation. Then you see we jump into R. This is an R. I'm creating a stand model here using R to create those 2 data sets I was talking about, the tweets with each of the topics for the tweets, and then the words for each topic. And then finally here, this last step, we're moving into deployment. So taking that model that we built and making it more production ready. All right, and so let's move into DSS. All right, so I'm just going to walk you through the different steps. I'll show you a little bit about the end product here. So I've created a little dashboard. So I've hooked up our Twitter API to Twitter. I've given it the keyword data, so it's listening for tweets coming in about data. So anytime you tweet about data, it's getting pulled onto my machine. I've run an LDA using Stan. And so each of these little circles here represents somebody who tweeted with the word data, and the color here represents the different topics. And I've just specified 5 topics in total. So that's an output, just monitoring Twitter. Yeah, you can see some other stuff, like this is the hour of the day. Really just showing you when my laptop has been open and closed today. So I was awake a little bit at 7 in the morning, and I was in meetings, and then I got more tweets. I just saw that. Yeah, and then the last thing, yeah, I guess I'll save that for later because we can't show that. All right, so let's start with the data acquisition. I know I'm doing what you said not to do, which is the first thing to go out and get a bunch of data, but that's exactly how I started this project. So what we have in DataQ is the ability to pull in a bunch of data from Twitter. Just to demonstrate that, I'll do that really quickly for you guys. So I'm going to create a new Twitter data set. Does anybody have a keyword that you want to listen for on Twitter? Stan?
Version.
Any other ones?
Trump.
No, that's the most.
It's producing everything.
We're doing it. Okay. All right. Anyways, you can choose the kind of stuff that you want to pull down to pull out the hash. Anyways, and so then basically this here makes your data acquisition process a lot easier. So I think a lot of times when you're working with big data, it's tough to get access to your data. It's tough to kind of figure it out and get access to it. This is trying to, so pulling down, most of them are about Trump. Trump spotted at Amy's barbecue. All right, cool. All right, so pulling down our tweets here. So this is the tweets that we had about data. So again, anytime somebody is tweeting about data, it's going into this data set. The next thing we have to do is we have to start cleaning that data to get it ready to format, ready for a format that Stan can use. And so you can either do that in code or with a visual interface. So I'm just going to walk you through really quickly how to do this in visual interface. All right, so again, here's the tweet ID. Here's the time that it was tweeted, the user who tweeted it, the text, et cetera, et cetera. We have to do a few things. So for instance, We can say, okay, I only want to keep English tweets. Then here, this is my raw text coming out of Twitter. Maybe I just want to normalize that, make it nice and clean. Maybe I want to then take this, split it into words. So those are the words that are going to go into my LDA processor, right? And then maybe I want to take this and then fold it so that I have one word for each line. Okay? Stuff like that. So really quick data prep, data visualization. Okay, just showing you how I'm going to clean this data, taking my raw data from Twitter, generating my words that are going to be put into my LDA from that topic model. Any questions on that? Yeah. So we can do a hack code. Anyways, so again, all the way up through here, this is just me cleaning the data, and so I finally get into my final data set, which has all of my words for a bunch of tweets. The next step here is actually running my stand code. So to do that, I'm using our R API. So what does this look like? So you've seen some stand code earlier today. I'm calling the R API where you can write stand code inside of R. Okay. So
you can only like stand inside of R, or you can use other things.
Oh, yeah, so the way that you would get native stand directly in this interface is what we have are these folders here. You can just upload arbitrary files. You can upload a .stand file into that folder and then tell R, this is where my file is. So that's actually probably a cleaner way to do it. I just hacked it. Yeah. Anyway, so here's our stand model specifying our LDA. The only thing, I know there's a lot of R users in the audience, so I just want to point out two quick things about our R API. What we provide for you is this DKU read dataset function, which will let you read data from our studio, and then similarly a DKU write dataset, which will let you write data into the studio. Okay. So I'm doing that. It's training my model here. So now I go to my next data set here. I have for each of my tweets the topic that they were tweeting about. So now I've taken my raw tweets and I've assigned them the topics. Okay. Specifically because Stan is Bayesian, rather than just assigning tweets, it's giving you for each possible topic the probability that the tweet was in that topic. So here, this first tweet, it was 33% topic 1, roughly 2% topic 2, 27% topic 3, etc. Questions on that? All right. I also created another data set which is showing which words are most associated with each topic. So again, 5 different topics, and then we can say, okay, which of these words are most likely to be seen in each of these topics relative to some sort of base understanding. So I think this is pretty interesting. So if we filter it, and we look at, for instance, topic 3, you can see tweets coming from topic 3. They're tweeting about personal trust and things like that. These are probably tweeting about their personal data and having trust in various companies. Topic 4 was also pretty interesting. So I looked at this and I was like, what is that? So cyber published medical and Nadal. And yeah, and then, so then I Googled that. Yeah, and then, yeah, so Nadal had his medical data released today. So that came out as a distinct topic in my analysis. All right. So that's kind of cool. Sorry. All right. And then basically, yeah, so that's pretty much all of it. So again, took all the data, I cleaned it, produced a stand model, got my topics out. So I found, okay, there's one topic talking about personal data, another talking about Nadal and his medical data, and then the other three are a bit murkier what they mean. And I guess I'll show you this final step that I did here. So there's Stan is great, and then I think it's the fastest Bayesian tool on the market by far. It's much, much faster than Bugs and Jags, so that's fantastic. I think, like we were saying earlier, there's a limitation where with this you can't scale it onto Hadoop. What if I had 100 gigabytes or a terabyte or a petabyte of Twitter data? How do then I take my topics that were generated with Stan, and how do I scale that to a much larger data set, right? And so that's why I'm mixing traditional machine learning with Bayesian stuff here, with Bayesian machine learning here. So we can see here, this is our data set where we have our topics with all of our tweets here. So being a non-Bayesian, I think, okay, I can just use this here as a target, this topic 1 here, and try to build a classifier, trying to classify my tweets into this topic just using traditional machine learning. So yeah, I don't want to just do a product demo, but I don't know what this turned into. Yeah, so to do that with DSS, you can just click on this topic and say, create prediction model. And click create. In our settings, going into my features, rejecting everything except for the text itself, which I'll input as text, and I'll say use TF-IDF vectorization here. Are you guys familiar with this type of NLP research? Okay, cool. Save that. Anyway, so what this is doing is I have my topics that were created using Stan. Yeah, topics that were used creating Stan. With full Bayesian inference, I take that, I assign topics to a small number of Twitter tweets, Twitter data. Then I can use traditional machine learning to build a model to classify things into those topics. Anyways, so basically that's pretty much it. So this deployment phase here is taking that data from Stan, using traditional machine learning to score a much larger Twitter data set, and then getting the final output through that. So again, so then here's the final output. People tweeting about data, the different topics. Topic 3 about personal data, topic 4 about Nadal. Again, overall, using DSS to get your data, clean your data, using Stan for Bayesian inference, traditional machine learning, scale it after that. Anyway, so that was super fast. I know we're all hungry and thirsty. So if anybody has questions, you can ask. Or yeah.
Yeah, I guess we can move on to the panel. And we'll have questions for everybody.
Okay.
Anyone that wants to stand up, you've been sitting for a while.
And we have Stan stickers here.
Wow.
It was all worth it. Auctioning.
You don't want to take it.
I did.
Well, yeah. We stand. Is there?
Well, you can stand.
Yeah. Why did I really don't see us? Is it possible to pass out here?
Yeah. Yeah.
Get drunk. Yeah. All right. If you participate, you will get a stamp sticker. If you don't, we'll have to find either me or Eric or Mike, and we'll give you a stamp sticker. I'm not gonna do a sticker. All right. Mike will not give you a sticker. You can still harass him. It's okay. I'm Daniel. That's Michael. You've got both Eric's. You have stickers. So, what's the format of this?
I have no idea.
Well, people ask questions really, so.
Is this being streamed?
It is actually still. So if you want to ask questions, yeah, I can shoot it out too.
All right, I'll need a beer first.
Non. Quelqu'un a des questions en fait pour nos invités. Vas-y.
Yeah. I am I use keyboard and then stand up.
Fine secret.
Yeah, fine secret. That was my question. They have now their own implementation of the notes that are using yellow, and you have yours instead. Is there some kind of benchmark between those systems?
This is sort of, but you'll see that Shay will be much faster. So piano's quite slow, and then it's symbolic. I don't know whether, or not, it's not ordered, it's a symbolic progression library. Mainly meant to be very useful for the kind of models that show deep learning. So the kind of use that you can get are not very generic. They can really scale up the kind of models that you build for something that you use in keyboard.
So quickly, the difference between symbolic differentiation and automatic differentiation. Symbolic differentiation operates on the actual mathematics, right? So the derivative of x squared, we know is 2x, right? We know that for a fact. Automatic differentiation works anytime you have the chain rule for any of the operators. So symbolic differentiation is limited to what you can symbolically differentiate, whereas automatic differentiation, you can differentiate anything that you can write down.
And but in terms of pure speed, in most cases, standard algorithm is made much faster than piano. The argument for something like IMC is that you can build a model with Python. The fallback, or the limitation of that is that Python, the full expressibility of Python is not compatible with something like differentiation. So you have to deal with the problem of what if those models are differentiable. How are they going to handle that? Whereas standard, that our language was built from the ground up to limit you to differentiable models. Right? So we tried to make this as user-friendly as possible so that you only build good models as much as possible. You can build lots of bad models, but we try to make it as hard as possible.
On the converse, anything that you can write in standard, you get gradient.
Yeah, and I'll just also say that the IMC developers were very kind to tell us they were going for a code and user implementation, which is what it's there for, right? All open source. But if you really want the cutting edge stuff, it's all that we can understand.
So we actually know the IMC developers and their friends, and they do good stuff. The usual flow is that we're doing the cutting edge research and implementation, and then they'll take that and port it to IMC. It hasn't gone the other way yet. I'm not saying it won't happen, but right now.
Yeah, sleeping.
Yep.
Hey, hi, Chris.
Est-ce qu'il y a une autre question pour nos invités?
Well, see, Edward's kind of a spin-off in some sense, right? So Dustin was working in our group. ADBI was done by him and Alpha. I don't know Alpha's last name.
No, we won't.
Okay, it's tricky. It's wacky. But two students at Dayfly, who at Dayfly were working on building this machine learning like algorithm. And Stan, very, very neat ideas up into it. Turned out to have some neat applications. What they're interested in is not so much building tools that work. They apply problems, they want tools to play around and just kind of see how it work and scale certain kind of problems. So they're more interested in tweaking the algorithms than tweaking the models. So Edward came out of their ability to tweak the models really fast and stand, because we're very heavily talking about C++, and it's kind of hard environment to develop in, unless you really know what you're doing. And so it's much easier for them to build something like Edward, where they can have all kinds of flexibility in the models they build, they can plug in piano, they do all kinds of all this stuff more amenable to that kind of thing. So, and I think that's when we first say this, Edward is very much a prototypical kind of algorithm development environment, where they're playing around with machine learning algorithms. Stan is much more for the identified problem and fit as fast as possible.
Just quickly before we go on, are we speaking too fast in English?
Well, no.
I thought we were using that.
I think maybe to be you're not speaking that fast.
Okay. I speak slowly, but we're tossing a lot of terms.
Une autre question, vas-y.
Well, I can do fun. So now we've heard from Eric that he's moving standard to production this way. What I'd like to hear from the standard about how much more movement do we expect, or could we expect on the language itself? In the past, I used to write arrows, that's equal time.
Is that great?
It was great, yes. So how much more movement is there? And so we go ahead to go to production.
Yeah, I think there's 2 or 3 things we're considering. But for the most part, it's solid. right? So I think if we're going to break anything, we're going to break it in Stan 3, not a version of Substan 2. So it's going to be a big version change, only a few small changes that have been strongly motivated by our users, or more importantly, by a lot of mistakes. And so this is a tricky thing. We want a language that's expressible, but at the same time is kind of facilitates building good statistical models, right? That's a really tricky ballgame, and in some sense it's an open pedagogical question. So there's a few things we might want to change. We're still debating it, but I would say it's probably like one or two things might change, but otherwise the rest of it.
Yeah, I agree. In terms of, so you're talking about production, we're always getting faster.
Where faster is one thing, the old code is one, that's correct.
Yeah, but again, if you pull out an old version, right, the old version will work, right? So it's all, archived. You can always pull out an old version and run it on the model.
There is a caveat. Under certain boundary conditions, it won't work. Like for example, we've made certain keywords, particular keywords, keywords now, and they used to not be keywords. So if you name something like pie, well, actually that works now.
I can't.
Target. If you name something target, you can't use it anymore. Yeah. But how can you name something target? And if that's a problem, you just rename it. Right?
But any kind of changes rolling out will deprecate early on, so you'll see it and know many months, if not years ahead. So we're not going to like pull the rug out of you.
You said that standardized proven on the data sets.
Oh, I don't think we said that.
No, we didn't.
We didn't say that.
We did not say any of that.
So next question.
So what is
There is.
All right. So the current limitation. So the question is, someone claimed that STAN does not work on very big data. The limitation actually right now is that it has to fit in memory in your computer. Now, if you have a massive machine, that's a lot of data. Right? If you have a small machine, that's less data. With that said, it would be easy to write an extension to query into the database. That's not impossible. We just don't have it yet because that's not our use case. For our use cases, for a book publisher, for a baseball team, for pharmacometrics.
Well, the beer is acting up on me. Oh, by the way, it's not beer, it's lemonade.
The placebo effect.
So for most of our problems, we don't have this limitation, right? A couple gigs of data, whatever, right? When you start talking about terabytes of data, honestly, I don't know what to do with terabytes of data. But when you have terabytes of data, the only thing that you can fit on that is a very, very simplistic, right? So what we're focused on is with less data, how much information can you extract from that data? How complex of a model can fit to that data that explains the data very well? In real life, in the problem that we work on, most of the time you don't have infinite data, right? For example, a survey for whether or not Trump's going to get elected, right? They have observations of 5,000 people. We're talking about 5,000 people, which are supposed to represent 50 states, all age groups, all income categories, all education levels, whether or not you, right? So all of a sudden, 5,000 becomes, in this one group, I might have one observation. He either said yes or no, or she. Right? So based on that much information, what do you do? And that's where Bayesian inference comes into play, and you get a lot of power.
So for a less political answer, what do you call scalable, right? There's Hadoop, there's Hive, there's all of the technology out there. What do? They count. They count really fast, right? What is parallelizable in a fundamental sense are linear operations. You cannot parallelize a nonlinear operation because by construction you have to be able to kind of aggregate it in an nonlinear fashion. And statistically, that means the only things you can fit on these scalable, quote-unquote scalable architectures are Gaussians, right? This is a fundamental limitation of what the architectures allow you to do operationally. So if you look at machine learning literature, what people claim in terms of scalable, subsampling, any kind of thing that either streams the data or parts of the data, or tries to make simplifications, MapReduce, all of these kinds of wonderful technologies. if it, as Dan said, very, very simple model, right? And there are certain cases where you have an abundance of data and you fit fast enough, you can get a reasonably good inference out of that. But if you start looking at the deeper data more deeply, you start seeing well, there's covariates, there's time dependencies, there's a lot of structure that you ignore. And so we're not focused on trying to get a linear model faster than anyone else. We're focused on trying to build more robust statistical models that allow you to capture more information in the data that you collected than you could have had before, right? So I think a lot of us are motivated for more scientific applications where you don't have 8 terabytes sitting on a disk and some manager says fit it. We're coming from very precious data, very expensive to collect. You really want to pull everything out of that. Now, there's a lot of industrial applications to that situation once you start looking at data more deeply. But you really have to kind of flip your head around and say, not so much, what can I do with all this data that's there, but rather, what's the question I want to answer, and what's the best way of answering that question?
The way I typically frame it is, if you want to make really, really fast predictions, like, there's a lot of interest in scanning metrics and like Federal Reserve banks and things like that. But there's not a lot of interest by high frequency hedge funds, nor should there be, right? And that's sort of like an extreme case scenario, but you can imagine there are lots and lots of use cases where I have like tons of data, we can make very, very fast, like Hors série prediction, like a point prediction or something like that. And I can't afford to wait and all that kind of stuff. And in those cases, it's just like, it's not our wheelhouse, it's not our volume, we're not really that interested. And there are lots of tools that do that, and so on. We really care about those cases where you really need the right answer, like, and you're willing to like pay for it in terms of like patience, mostly, and some learning curve, like where the decisions are really, really important. So that's where we see Stan being adapted. Like Stan gets adapted first in those situations. Like pharma companies like it because the decisions they make to approve drugs or to figure out the right dosings are really important for people's health, right? Like Federal Reserve Bank, we have in New York, really cares about getting interest rates right. They don't need to know them right now, but they want to get them right eventually. And so on. The baseball team really wants to know how much they should pay for a player, or what is that latent ability parameter for a given player, because it's really expensive for them to be wrong. In those cases, you really need to see it anywhere else.
I mean, I guess to flip it around in another way of saying the same thing again and again. Stan tries to be generic in that it's something like Hamiltonian Monte Carlo or the tools we use, try to exploit information in generic fashion. You build a model, we'll let everyone get the information we can out of that to fit it as fast as possible. To do any better, we need to exploit very specific structure of the model. So a lot of these scalable machine learning algorithms are exploiting simplifications they assume hold in that model. And if those simplifications hold, great. Huge speed ups, take advantage of that structure, awesome things happen. And if they don't hold, you get biases, you get odd uncertainties, things become a little bit more fragile, right? So we try to be generic as possible. We're coming from that front. Other tools are coming from the other front, and they can all be compatible and complementary in the right way, so long as we recognize the assumptions that go into them and kind of what they're meant to be used for.
One particular example is LDA. If you ever want to implement LDA, don't use that. Go use Vocal Rabbit. It's a package, and it's the fastest thing for your client. It'll be faster than what you can do personally, and it'll be faster than saying by a mile on this particular model. The question is, what happens when you want to extend your LDA? Right? As soon as you deviate from the model that you implement, you have no choices.
D'autres questions? Oui, vas-y. Can you repeat the question?
Yeah, the question is, does Stan deal with copulas, sort of? Copulas are kind of wacky statistical objects. There is one dev who plays with them a little bit. And I think if you look on the Stan users list, you'll see some bits here and there about copulas.
There's also a new R package called Copula VTA that implements using Stan, which you can implement the copula in Stan. That's no question. The question is how well will it fit, how well does it describe your model. Those are all questions. It depends on your data, depends on how complex your model is,
I mean, there's CDFs, there's transforms, so you can kind of construct your own copy of it. You don't have tools built into that.
What that means is that if you looked at any statistical paper and you find a distribution that's not defined in standard, you have the power to just write it up. There's no limitation. That means any arbitrary model, anything that we don't have, it's fine. You can do it.
Une autre question? Oui, au fond.
Didn't they use Bayesian inference in coding?
Well, yeah, so
You repeat the question.
the question is, are they using or have they used Bayesian inference in polling before, or are they already using it? Yes and no, right? So most of the polls that you see in the public don't actually use that much Bayesian inference. A lot of the private polls that people make money off of are very much using Bayesian inference. The Obama campaign used a lot of Bayesian inference. For example, one of the reasons they had a lot of success in getting early donation and voting going on early on. So yes and no, right? So I mean, certainly Andy Gelman, who runs STAN, has done a lot of Bayesian polling design, multi-level regression, course application, very, very powerful tools. But even going 2 weeks ago, or a few months ago now, to the Brexit, right? Most of the Brexit polling was just flat out standard polls, right? They had standard errors. They would plot whatever the response was. There was no correction for the response rate. There was no correction for the covariance. There was no post-stratification, and you saw huge biases, of course. That screwed a little bit. Whereas if you look at YouGov, was doing this kind of like on their blog, this multi-level regression post-stratification Bayesian version, which actually was consistent with what happened, right? So you do kind of see people toying with these techniques, but I think it happens a lot behind the scenes.
So the YouGov predictions were for Brexit?
Well, so there was the official YouGov prediction, that was kind of the public one, and that was the standard polling design.
Okay.
And then Doug Rivers on and someone else on the YouGov blog was doing this kind of Bayesian design. It was kind of just a fun, here's this other thing that we tried.
Okay.
But it wasn't super well publicized. It was an odd thing.
Well,
They had much larger uncertainties that took into account the fact that the YouGov polls are kind of notoriously bad at sampling outside of London.
okay. Yeah.
London started started out of London. But it did a reasonable job of post-ratifying and getting good uncertainties. And people just didn't harp on it after that.
Okay. Une autre question?
It's possible to use the GPU.
You can use that.
Next question.
So no GPU support. With that said, there's a caveat. Last week, I implemented on parallel CPUs, and we use the Eigen C++ library, and that actually has GPU support. So if you're a very good engineer, not a data scientist, not a computer scientist, if you're a very good engineer, you can figure it out. If you do, please tell us.
No, but again, like GPUs are this very specific operation. You have to have very low I/O overhead. You have to have the right kind of fast linear mapping out with production. And if you're really good, you can tune these things. We talk like anybody who's in GPU as well. They spent years tuning that to make it work, right? Because STAN is so generic, it's very hard for our field to identify kind of structures in the model to figure out when to apply GPUs if they're not to. We love to do multi-threading. We love to do SPI or OpenMP, right? But even that is hard. Like, when in a loop can you identify what's parallelizable and what's not? How do you get the automated work with that? And there's, like 4 full-time employees and, kind of maybe 10 full-time equivalents. So we just don't have the manpower.
We have like 3 full-time and about 40 contributors.
Yeah.
So it's 2 full-time employees, and then Michael's about half.
Well, in a week.
Yeah, it's about half, and then like the rest of them contribute to about half. Right?
Yeah.
So we don't have that many people. It comes down to me, Bob, Michael's next, and a few others.
But the point is, if you want to join us,
Yes.
and write your GPU code.
All right. So just if you didn't catch it, we're all open source. Anyone in commercial industries, the basic STAN libraries are BSD licensed, so you can use it commercially. You don't have to tell us. We like it when you tell us, but honestly, it doesn't matter. We'll use it freely. We'll use it openly. We take contributions and most of our discussion is all open. Like, we like openness. Now everybody gets a sticker.
It's raining.
Une question au fond. Vas-y.
I would like to know if you have some design you will regret.
Alright, so the question is, are there any design decisions that we regret? Okay, so one that's going to be an unpopular opinion is that we introduced the sampling notation from bugs. So anyone that uses bugs and jags, the tilde, like that, we actually regret.
That's
Yeah, so it's
Some of
not-
you regret.
Some of us regret, right? Any other decisions? Everything else?
That's corrected.
The underscore log for density is just bad.
Yeah, that's one that's bad.
Okay. Oh, so okay.
Oh, actually, the ODEs, the why didn't we use vectors? We probably didn't know.
Is it a raise?
Yeah.
Oh, that's fine. I think like the naming of a lot of the functions, inverse logic, worst.
What is that?
It's not just called logistic, right? Like if they're all named after the link functions, it's atrocious.
Why don't you just add logistic?
Well, because that would confuse things. I don't want to support other functions.
We should find it out right here.
Yeah, exactly.
And he said ODE. Now, those of you who come from pharma may know scan for this, but the rest of you probably don't. And this is one of like the really cool features of scan that you probably haven't heard of, which is to say that in scan you can actually you can write down a ordinary differential equation, and you can fit that thing to a you should fit parameters in that thing stochastically, which is kind of amazing. So people in the pharmaceutical industry in particular are using it because they have scientists who understand the drug diffusion process well enough that they can write down the actual differential equation for the drug process. And so they have these like really cool patient level models now. This is like really nice, right? You actually ultimately want the medicine to be at a patient level, so they're doing it now. But any dynamic system for which you have enough understanding to write down that equation can be specified in scan, and it's like, you know, it looks kind of magical. And so if you have some familiarity with ODEs, just play with that in scan. You have lots of fun.
Or just a quick poll. Who's used ODEs to fit models? One.
All the pharma
Two.
people.
All right. So I won't ask the next question.
Yeah, full system.
Yeah, full system.
Yeah. So kind of arbitrary size. I mean, we use state-of-the-art solvers, so you're going to get the best combination possible. Yeah. So from any ODE built in, even specifies some first order differential equations.
Even the stick ones.
Yeah. So we use CBOD, actually CBODS, but kind of the state-of-the-art in terms of syssolving. No. That's the whole other.
You're being greedy.
We are talking about DAs. So.
Yeah. So the nice thing about ODEs is there is a solver. There is no a solver fees. That's the whole of the bulkhead.
Lucas, you're weak.
How about the continuous velocity? I saw some slides about the fidelity of the lots of impacts. I know that there is a lot of cover and time. Also, we want to fit the model and sometimes the model doesn't.
Yeah.
And how that's compared to the X?
Yeah. So this is my will. This is what I do for research, right? So I'm a postdoc in the UK, and I kind of study theoretical properties of HMC with colleagues. And the thing about MCMC that no one kind of emphasizes is that it doesn't always get the right answer. Yeah. Right? You can run it, and it will give you a wrong answer. Yeah. And this is very bad. Yeah. And the problem is like the samplers, like especially give sampling and like random walk metropolis, they're used a lot in WinBugs, JAGs, etc. They are not particularly robust, and they fail a lot on a lot of models, right? So Hamiltonian Monte Carlo is what we use in HMC. It's a much more sophisticated algorithm. We can show mathematically with papers in the archive and submission kind of showing properties are much more robust. They will work on many more models than other samplers will. But here's the really big part. When it doesn't work, there are strong diagnostics of why it doesn't work, right? So in other words, when you run STAN, you'll see all of these warnings that pop up that say divergences or big fractions of information. These are very powerful indicators that you should not trust your data. Right? So it's not perfect. It's not saying that we're always going to be able to identify when this is work, but we are head and tails above any other sampler and identifying when there's potential bias, right? And this is cutting edge work, and it comes from just the nature of HMC. It's really, really cool. I'm really excited about it. Right? So these things are all in STAN, right? Right? This is, we're talking about STAN versus IMC. IMC is great, but it take a while for them to adopt these things. If you run STAN right now, it will yell at you more than any other sampler will, right? That's a good thing. And then of course there's things like split R hat, which is kind of very generic, scale and Rubin statistic, which gets run. That's another thing that you can look at. And so we spend a lot of time trying to teach what diagnostics to look at, how to test your model, what you should be looking for. But there's a plethora of information out there.
Sometimes to have a lot of diversity, and sometimes for one diversity, the model is
yeah,
for all of them.
Yeah, it's got to be all of them.
Yeah.
So the thing about these diagnostics is that they all work. Even if one of them doesn't work, it's a sign that you failed. Right? MCMC is really fragile. So they all have to work. They all have to pass. I know sometimes you want to be like, well, that one, it's only sort of failing. And I kind of ignore that. Nope. Yeah, take it. Okay.
So how many people here are familiar with MCMC methods and have actually implemented them? It's okay to say no, right? So how many of you have used optimization? Right, and know how optimization works. So that's about half of you. It's sort of like, I don't know, convex optimization versus non-convex optimization, right? So if you do non-convex, you can't guarantee a solution. If you do convex, you guarantee a solution, right? It would be nice if a non-convex solution told you it was wrong, right? Instead, we have these diagnostics that tell you exactly when you're wrong.
Almost always.
Almost.
We're still working on the proofs.
Yeah, but at least it will tell you when you're wrong, for sure. The problem with the old MCMC methods is that they'll run and they won't tell you. Right? You don't know. You just have no idea if they're wrong.
And we know a lot of examples, like Harkin model is canonically back for this, right? If I put a Harkin model in a standard parameterization with bugs, you get terrible answers, you change it stuff. Right? That's fun.
So I have a question. Right? Yeah, for data IQ. Why didn't you run this in PyStat?
Yeah, I could have, but I'm just not a programmer. So
okay, so he's an R programmer. There's Python. What else do you have?
We also support Bash, so if you want to do command line.
All right, so there's command stat. What else? Do you do MATLAB?
This is a loaded question.
I see what, no, we don't support MATLAB.
MATLAB, Mathematica. Where's Vincent?
Hey.
Thank you. He did Mathematica, Stan.
Stata?
No, no Stata.
Yeah,
Julia?
These are all smart choices.
Yeah. No Julia.
Okay, so Python and R and Bash.
Yeah. So we do, yes. Yeah. So we yeah, so
how many kernel extensions are you using?
It may be a bit tricky, yeah. So visually supported languages, SQL, Mala, Hive, Big, Scala, the variants of Spark, so PySpark, RSpark, Scala, Spark, SQL. I think that was all of them. R, Python, Bash. No, well, not in the flow. You can't construct the data processing stuff in Java.
Really? Okay.
Des autres questions? Vas-y, toujours pas.
Yes. Good question. We just announced it this morning, about 1:30 a.m. local time, because I announced it. January 21st. It's in New York City. So if you want to take a trip, you know, both, I think all three of us would be there.
Yeah.
You want to go? All right. So anyone that wants to come, we have a conference coming up on January 21st.
So it's a one-day conference.
Monday.
It's not very big.
Yeah, we'll probably have a few stand classes that will precede it. So we'll do like a Thursday, Friday, like standard classes and management, full day conferences.
And the conference is going to show you different applications, and we might talk about the internals.
Yeah, we'll kind of figure it out. But I think the big thing is that we'll have contributed talks. They will not be talks. They won't be posters. They'll be like knitter docs and markup and Jupyter, right? So you're going to submit an actual kind of statistical workflow that demonstrates a cool idea or a cool application, and so everyone can run it and play with it. So we're trying to go more interactive and really take advantage of a lot of these people.
So that's another big point about STAN. We're not just about openness. We're about reproducibility. You write a STAN program, you can hand it off to anybody else, and they will be able to reproduce it.
Yeah, there's a lot of scientists on this thing.
Vas-y, vas-y, vas-y.
Oh, we have lots of questions about optimal design experiments. That's a modeling question. Yeah, it's not an ODE question. Really, how do you model this stuff? And the answer is you need to know what you're modeling.
I mean, so again, STAN is a concept programming language. We do not tell you how to build a model. That's what you can provide. Now you can use STAN to experiment with models. You can do power calculations. You can do a lot of tests and whatnot. But it's kind of yeah, sure.
Is that time?
Yeah, it's the gone time for the end. Allez, une ou deux questions encore, et puis après on pourra parler directement chacun de nos speakers directement. Vas-y.
Okay, so a very technical question. What does STAN stand for?
So, no, it's not an acronym. STAN is not an acronym. Whatever Andy Gilbert says, it's not an acronym. It's officially named after Stanislas Louis, who was a Polish mathematician in the Manhattan Project. It's in the US in Los Alamos, right, before the big bomb. Monte Carlo, in general, was a technique developed in that wartime project for simulating these neutron bombs. In fact, they used a truck. So there were no computers back then. There was no R. So what you do is you take a truck with a pen, a table of random numbers, and you would run the truck around simulating this neutron path. And that's how they made this really big boom, right? And so the original papers came out, and it was Nick Metropolis and Samuel Ulam really built mathematics. So Andy knew understand as kind of a fun, nod to history. They'll also claim he named it after the Eminem song. It was one of the first.
No, well, that is.
And then that, yeah.
So
you're still being recorded.
yeah, that's fine. This is semi-public knowledge, right? So one of our main developers, his name is Bob Carpenter. He's awesome. He's from Detroit, and Eminem is also from Detroit. Yeah, and Eminem has that song STAN. So that's the second.
And Andy Gilman used to go give talks. He would play Eminem. I think we put Lose Yourself or the actual song STAN before the talks. And for like 5 minutes, people would look at him like, nobody knew what he was doing. It was really weird and awkward, but that's a good.
But that's part of the story.
Yeah. So it's kind of a weird amalgam of a bunch of stuff. So it's a fun name, but it's not an acronym.
Oh, yeah. So all of you have seen STAN now. When you spell STAN, it's capital S, lowercase t, lowercase a, lowercase n.
Look at your t-shirt. Look at your t-shirt.
Okay, but there's capitals like lowercase. It's not clear what's what.
Yeah.
Also, these are the old shirts.
These are the old shirts.
These are vintage legacy.
But it's a name. It's not an acronym.
Yeah.
Okay. It looks like we've been talking about it for 4 or 5 minutes. It looks like a very touchy subject.
For anyone listening.
Yeah. Okay. Yeah.
All right, let's calm down, buddy.
It's okay. It's STAN. Okay. We get it. Okay. Une dernière question? No? Okay. Thank you for our speaker.
Merci à Data Écoute de nous avoir accueillis aujourd'hui. Donc, on a fait ça un peu avec eux. C'est vraiment eux qui ont tout organisé, en particulier Olivia. Demain, on a un deuxième hors série pour le Paris Machine Learning Meetup avec H2O, Scalable Machine Learning avec H2O. Donc, ce sera à Murex. Merci encore d'être venu. Olivia, si tu as des choses à dire, vas-y.
Not much more. I think we're all really hungry. I'm gonna go and get the food.